Hello, this is Dr. K. In this video, we're going to talk about how SSL and TLS work. These technologies are what web applications use to enable secure communications over the internet and to ensure confidentiality and data integrity. The description here is based on one section in the security chapter of the book Servlet and JSP, a tutorial by Buddy Kurniawan. SSL, Secure Sockets Layer, and TLS, Transport Layer Security, are cryptographic protocols used in web application security to ensure privacy and integrity. SSL was developed in the 1990s by Netscape. Technically, SSL is deprecated and TLS has taken over. But since TLS can be seen as a more secure variant of SSL, a lot of people just continue to use the term SSL. To understand how SSL and TLS work, we need to understand both symmetric key and asymmetric key cryptography. Symmetric key cryptography works when two parties share the exact same key, which is used to both encrypt and decrypt a message. Let's say that Violet, represented here by the purple glasses, wants to send a message to Mr. Blue, represented by the blue glasses. So Violet has a message, and she encrypts it using her secret key, a key that is shared by Mr. Blue. Note that the terms secret key and symmetric key are used interchangeably because for symmetric key cryptography to work, the key has to be kept secret by both parties. Back to our example. Now that Violet has encrypted the document, she sends it to Mr. Blue. Mr. Blue uses the secret key to decrypt the document. He does this by simply reversing the process that Violet used to encrypt the data. In the same way, Mr. Blue can send a message to Violet. Secret key cryptography is relatively fast, so it's a great way to pass data between two parties over the internet. Secret key cryptography is one of the oldest forms of cryptography. Even today, it remains the technique that is most widely used to encrypt messages. But there are some problems with secret key cryptography that cannot be solved without help. The biggest of these problems is that both parties have to have the same secret key before they can start communicating securely with one another. Since the key has to be secret, how do you send that over the internet without somebody intercepting it? Another problem is that everyone on the internet wants the ability, at least potentially, to communicate securely with everyone else. That implies that each pair of people has to have a secret key. That's a lot of secret keys needed. Finally, if you don't know whether your initial request is going to be intercepted by a bad guy, how do you know that the entity responding is really who they claim to be? Fortunately, public key cryptography can be used to address these issues. Public key cryptography, also called asymmetric key cryptography, is a harder concept to grasp than secret key cryptography, but if you keep in mind that fundamentally it's still about a sender that encrypts a message and a receiver that decrypts a message, you should not have a problem grasping it. In public key cryptography, one of the parties generates a pair of keys. Each of these keys can decrypt a message that has been encrypted by the other key. You see two keys here. So the silver key can decrypt messages that were encrypted by the blue key, and the blue key can decrypt messages that were encrypted by the silver key. One of these keys is chosen to be the public key. The public key is available to anyone who wants to use it. The other key is the private key. The private key must be kept secret from everyone except the owner in order for this technique to work. Recall what we said earlier. In public key cryptography, one key can decrypt what the other key encrypts. We will now look at the implications of this in both directions. First, consider that Violet has Mr. Blue's public key. If Violet has a private message for Mr. Blue, she first encrypts that message with Mr. Blue's public key. The encrypted message is transmitted securely to Mr. Blue. Mr. Blue can then decrypt the message with his private key. And finally, Mr. Blue can read the original message. Note that this same sequence can be accomplished from any sender with Mr. Blue's public key. The messages sent can only be read by Mr. Blue. Now let's look at what happens when a message is sent in the other direction, when a message is encrypted with the private key and decrypted with the public key. Suppose Mr. Blue has a document. He encrypts the document with his private key. Then he sends the message to Violet. Since Violet has Mr. Blue's public key, she can decrypt the message and read it. However, Violet is not the only one with Mr. Blue's public key. The key is public, so everyone who wants can access it. Therefore, it's not only Violet who can decrypt the message, but really anyone who wants to can get the public key and decrypt the message. This may not seem very useful, and from the perspective of privacy, it's not very useful. However, it does tell us something important. It tells us that Mr. Blue was the party that encrypted that document, because Mr. Blue is the only one with the private key. And this is the basis for authentication. Public key cryptography in this direction allows people to verify that the document came from Mr. Blue and not from anyone else. This kind of authentication is the basis for digital signatures.